Hello and welcome to this video on the motor effect and Fleming's left-hand rule for GCSE Physics and Combined Physics, higher only. And don't forget to like and subscribe. A wire in a circuit with a current flowing through it has a magnetic field around it. The shape of the magnetic field is concentric circles. The strength of the field can be increased by increasing the current, coiling the wire into a solenoid, and adding an iron core. In between two permanent magnets is a magnetic field running from north to south. If a wire in a circuit is placed in that magnetic field and the circuit is switched on, then the current carrying wire will have a magnetic field around it. The two magnetic fields interact. This causes a force that makes the wire move. In this example, the wire will move upwards. To have this motor effect, the direction of the magnetic field of the permanent magnets, the direction of the current, and the direction of the force must be at right angles to one another. Fleming's left-hand rule is a method to predict the direction of the force on the wire if the direction of the current and the direction of the magnetic field are known. The thumb represents the thrust, which is a force. The first finger is the direction of the magnetic field from north to south, and the direction of the current from positive to negative is represented by the second finger. In these examples, you can see that the magnetic field is running from north to south, which is from the right of the screen to the left of the screen, and the current is going back into the screen. And if you use your Fleming's left-hand rule, you'll find that the direction of the force is upwards. If we switch the current so the current is coming out of the screen, then your Fleming's left-hand rule will show that your force is going to go in the downwards direction. If we then change the direction of the magnetic field so that north to south is going from the left to the right of the screen, and the current is still coming out of the screen, then the force will be in the upwards direction. And if you flip the current again so that the current is coming out of the screen, then the force, according to your Fleming's left-hand rule, will be in the downwards direction. The force on the wire is caused by the repulsion between two magnetic fields, one from the permanent magnets, the other from the magnetic field around the current-carrying wire. If the field around the wire can be made stronger, then the repulsion force will also be stronger. The magnetic field around the wire can be made stronger by increasing the current in the wire and increasing the length of wire in the permanent magnetic field. The repulsion force can also be increased by increasing the strength of the permanent magnets. With stronger magnets, the field lines are closer together. These field lines are called lines of flux, and when they are closer together, there is a greater magnetic flux density. Stronger magnet equals a greater magnetic flux density. The factors that will increase the force in a current-carrying wire in a magnetic field are related by the following equation. Force equals magnetic flux density multiplied by the current multiplied by the length of the wire, or F equals BIL. The units here are force, F, is in newtons, capital N. Magnetic flux density, capital B, is in teslas, capital T. Current, I, is in amps, capital A. And length of the wire, lowercase l, is in meters, lowercase m. Questions using this equation are likely to need unit conversions. Common conversions are as follows. Milliteslas to teslas. Milli is 1/1000th, so to convert from milliteslas to teslas, divide by 1000. Millimeters to meters, divide by 1000. Milliamps to amps, again divide by 1000. Microteslas to teslas. Micro is 1/1,000,000th, so to convert from microteslas to teslas, divide by 1,000,000. A 5 centimetre coil of wire carrying a current of 1.2 amps feels a force when it's in a magnetic field. Calculate the force on the wire. The magnetic flux density is 0.3 teslas. Which direction will the wire move? First of all, we need our equation. Our equation is force equals the magnetic flux density times the current times the length of the wire, or F equals Bil. Now we need to convert our length from centimetres into metres by dividing by 100, and that gives us our length of 0.05 metres. Now we can substitute in our numbers. So F equals 0.3 multiplied by 1.2 multiplied by 0.05. And that gives us our final answer of force equals 0.018 newtons. For the second part of the question, which direction will the wire move? For this, you'll need to use your Fleming's left-hand rule. So your first finger will be going from north to south. Your current finger, your second finger, that will be coming out of the screen as your cell has got the positive side, the longer side of the cell is the positive side, and that will show you that your force goes in the upwards direction. And that's everything for this video. Thank you so much for listening.